Hello, everyone. Today we have our very own co-organizer, Mitsuki Hanada from UC Berkeley, giving a talk. Before we start, let us remind ourselves of the guidelines. We're all learning, everyone has something to contribute, and no one has all the answers. With that, let us hear Mitsuki talk about the Garsia-Procesi ring and the monomial basis. Take it away.
Thank you for the introduction and thank you for having me. Today, I will be talking about constructing a charged monomial basis of the Garcia-Procesi ring. So before we start, let's go over some definitions. So in this case, we're denoting all our standard Young tableau in French notation. So the bottom row is going to be the longest row. The reading word in this case is just going to be we read the rows from top to bottom, left to right. So in this case, the reading word of the standard Young tableau of size 321 is 6, 2, 5, 1 through 4. So if we take a standard Young tableau and take the reading word, we end up with some permutation and one line notation. And then we denote the set of all standard Young tableau of size n meaning there's n boxes, as subscript n. By the RSK correspondence, which we heard about last week, we know that we have a nice bijection between permutations and pairs of standard Young tableau of the same shape. We denote the first tableau PW and we refer to it as the insertion tableau, and the second tableau QW is going to be our recording tableau. And then one nice basic algebraic combinatorics result is the number of permutations of a certain insertion tableau corresponds to the dimension of the irreducible representation indexed by that partition because they both equal the number of standard Young tableau of that shape. So now before we talk about our Garcia-Procesi ring, we first need to talk about the coinvariant ring picture. So if we have a polynomial ring and n variables, there's a very natural aside action permuting those variables. We define the coinvariant ring to be this polynomial ring quotiented by all Sn invariant polynomials with no constant term. So we can think of the ideal generated by elementary symmetric polynomials. Yeah. So now that we have our definition, we want to talk about properties of this ring. So because it's a graded vector space, the grading given by the grading of our polynomial ring, we can talk about its Hilbert series, which is the graded version of dimension. In this case, the Hilbert series of our coinvariant ring is given by the Q analog of n factorial. So this expression here, if you substitute Q equals 1, we're going to recover our classical factorial. This ring is also a Sn representation because we have this very nice Sn action permuting the variables. And since we're quotienting out by an Sn invariant ideal, we still have that the quotient has an Sn action. So whenever we're talking about symmetric group representations, we can talk about something called its Frobenius character. So this basically takes a representation V and encodes the decomposition into irreducibles into a symmetric function. So it takes each copy of the irreducible indexed by lambda to the Schur function S lambda. So for example, we have here the Frobenius character of this Sn representation, which is just the defining representation of S3, decomposes into two different irreducibles. So the resulting Frobenius character is going to be this symmetric function, where we have one copy of the Schur function indexed by 2, 1, and one copy of the Schur function indexed by 1, 1. I'll just start. It's not quite the defining because I have sign here instead of trivial. Since our vector spaces are graded, as we were saying, we can have a graded version of this Frobenius character. So in this case, our graded Frobenius character is just exactly what you would expect. It's the Frobenius of each graded component, where the Q exponent is keeping track of what degree component you're looking at. So for the covariant ring, we can write our Frobenius character as a sum over standard Young tableau, and you take your exponent to be either the Madge statistic on standard Young tableau or the co-charge statistic on standard Young tableau. So there's this nice combinatorial way of seeing the Frobenius character of this covariant ring. But our whole point of the talk is to talk about monomial bases because I'm going to be introducing a basis of the Garcia-Procesi ring. So let's first talk about monomial bases of the coinvariant ring. So we have two very well-known bases, the Artin basis and the descent basis. The Artin basis is defined like this. The main takeaway you want from this is you can see that it corresponds to inversion just from what we have here in the product formula. What I mean by it corresponds to inversions is the degree of the monomial indexed by sigma, some permutation, is exactly just the inversion statistic on that permutation. So each of our basis elements are indexed by permutations, and the degree is given by the inversion statistic. Similarly, our descent basis is also indexed by permutations, but now our product is looking slightly different. If you know your symmetric, or if you know your statistics super well, you can see that this corresponds to major index, which is a bit more subtle than inversions. It's just you take the sum of the index at each descent. So in this case, if you look at the monomial indexed by sigma, the degree of that monomial is going to get the major index with that permutation. So we have two different monomial bases, both are indexed by permutations, and both correspond nicely to certain permutation statistics. And when I say correspond, I mean the degree corresponds to that permutation statistic. Once again, if you're super familiar with your permutation statistics, in VinMaj we're super nice because they both are Mahonian, meaning they have the same distribution given by the Q analog of n factorial. So what I mean by that is if you take the sum of all permutations over all permutations and you record their in VinMaj, you're going to get the Q analog of n factorial, which is exactly the Hilbert series of the coinvariant ring. So immediately you can see that in each degree, we have the right number of monomials in either of these bases in order to actually be a basis of the coinvariant ring, because it matches the dimension in each degree component given by the Hilbert series. So we can say here that these two bases are compatible with the Hilbert series in this sense. You can sort of immediate that we have the right number in the right places. Any questions so far?
So the bases are indexed by the permutation values and not the positions.
They're indexed by they're indexed by permutations, like in one line notation.
Yeah, but yeah, but the subscripts are not the positions, but they are what the
Yeah,
value in that
yeah.
position is.
And the value in the position, yeah, exactly.
Interesting. Okay.
Anything else?
I have kind of a silly question. Maybe this is why is the coinvariant ring R sub, I mean, why this notation R sub 1 to the n?
Well, that's an excellent question. We're going to be leading right into that. So let me go forward to answer that question. So now we're going to be talking about the Garsia-Procesi ring, which are quotients of this coinvariant ring. So I give a definition here, but the definition itself is not that important for the sake of our talk. All you need to know is there's some ideal that is indexed by a partition. If you quotient out your polynomial ring by that ideal, you end up with a quotient not of just the polynomial ring, but of the coinvariant ring itself. And if mu is equal to the column partition, so 1 to n, then R mu, the Garsia-Procesi ring corresponding to it, is just a coinvariant ring, which is why we've been using this clunky notation for the coinvariant ring, because secretly we've been talking about the Garsia-Procesi corresponding to a column. So that's to answer Anastasia's question. And we also have that this is still an SN module under the action permuting the variables, because the ideals we get are still going to be SN invariant. So I guess on like these quotients also arise naturally in geometry. So our coinvariant rings are cohomologies of the complete flag variety. So if you take the complete flag variety, look at its cohomology ring, that's isomorphic to the coinvariant ring as graded algebras. The Garsia-Procesi ring is the cohomology of Springer fibers, which is a subset of our complete flag variety. So there's sort of the natural quotient to consider when looking at this polynomial ring, both in terms of like as polynomials, but also from like a geometry perspective. They're super nice. They're indexed by partitions, and they're going to be quotients of our coinvariant ring. So I guess, yeah. So before I continue, the sort of buildup that's going on here is we have our coinvariant picture. We now have these quotients, Garsia-Procesi. Can we find monomial bases of the Garsia-Procesi using the stuff we already know about the bigger space, the coinvariant ring? So before we ask ourselves that question, let's first talk about the Hilbert series and the Frobenius character of this SN module. So we actually have a very nice formula for the Frobenius character for these things. They're given by the modified Hall-Littlewood polynomials. So if you're not familiar with that, one more, I guess, well-known formula for these is it's a sum over semi-standard Young tableau of weight mu, and then you take q to the cocharge s to the shape. But there's an alternative equivalent formula given here by Lascoux, which instead of taking the sum over all semi-standard Young tableau of a certain weight, we take the sum over all standard Young tableau, satisfying a certain condition called the C-type condition here. So it's going to be some sort of partial sum over all standard Young tableau, not quite all of them. We're going to take q to the charge, and we're going to have s to the shape of the transpose standard Young tableau, where this symbol here denotes the dominance order and partitions of phi prime. So the reason why we're choosing the standard Young tableau version instead of the semi-standard Young tableau version, which is more familiar, is if we remember what the Frobenius character of the coinvariant ring was, we could rewrite it into this formula using charge and transposes. So you can see here immediately that if we choose to write our modified Hall-Littlewood polynomials like this, we get a summand of the full Frobenius character of the coinvariant ring, which sort of highlights how this coinvariant ring is the bigger space containing our Garsia-Procesi. But there are a few things in this formula that I haven't actually defined yet, namely what is charge, which I think a few people in the audience are probably familiar with, and what is a C-type condition. I think it's more of yeah, it's more opaque in terms of what we're talking about. So I'm going to go over both of these components. Yeah, I guess one thing to note before we do that is if we have our Frobenius character, we can obtain the Hilbert series using symmetric function things. But one thing to note is we can now write it using a similar sort of formula where we have standard Young tableau and we have a C-type condition on the standard Young tableau. So we've just rewritten it in the most natural way we can. We're going to further simplify it once we know some things about charge. So what is charge? So charge is a statistic on permutations. It's defined on all words of partition weight, but in this case, we only care about permutations because we are only caring about standard Young tableau. For any permutation, we can construct something called its charge word by labeling each letter in our permutation in the following way. So we first label 1 by 0, and then we keep labeling the numbers in order. But if we label I by k, we label I plus 1 by k plus 1 if it's to the right, and k if it's to the left. So this corresponds to, if you take our word like this, you're reading the word from right to left. Each time you circle back to the head, you're going to add 1 to the index. So we start with this word, we start with 1, we label it 0. We move to the left, we read 2. We haven't returned to the head of the word yet, so our index is still the same, we label it 0. We continue throughout the word without seeing 3 until we have to head back to the front. Since we have to head back to the front, we add 1 to our index. So now we have a 1 here. We keep reading the word from right to left to look for 4. We find 4 at the end of the word, so we add a 1. And then finally, we can't proceed forward to the left because we're out of letters, so we have to return back, adding 1 to our index, and then we see 5. So then we get that, has a label 2. So using this sort of like searching algorithm, you can label each of the letters in our permutation to get the charge word of the permutation. The charge statistic of a permutation is just going to be the sum of these letters in the charge word, and the charge of a standard Young tableau is just going to be given by the charge of the reading word of the tableau. So even though here I've only defined how to construct the charge word of a permutation, we can use this to define the actual statistic on the permutation, as well as define the statistic on all standard Young tableaux as well. So some things that are nice about charge. One thing to know is charge is secretly major index, where remember major index is that permutation statistic that came up earlier when we were talking about the descent basis. So the charge of a permutation corresponds to major index of a different permutation where you make modifications using reversing the word and then taking the inverse. And then if two permutations have the same insertion tableau, so via RSK, if they correspond to the same tableau in the first coordinate, then the two permutations need to have the same charge. So then I guess one thing to go back to is here we define charge on standard Young tableau using the reading word, but we could have just used any permutation that had P or T as its insertion tableau to define charge on tableau. And then using these properties, we can rewrite our Hilbert series. So we take this statement about charge of tableau and rewrite it to a statement about charge on permutation. The nice thing about writing it in this way, once again, is we want to have that sort of parallel with the Hilbert series of the coinvariant picture, which was a sum over permutations raised to Maj or raised to charge. Here, now we have a partial sum. We have a sum over certain permutations that satisfy a condition given by C type, and then we have Q to the charge. So now our Hilbert series and a Frobenius character both sort of look like what they should. They look like summands of the full Frobenius and Hilbert series for the covariant ring. And we still don't know what the C-type condition that's floating around has been. So the C-type is, or the catabolizability type of a standard Young tableau is a tuple that we compute in the following way. So we take a standard Young tableau, we find the largest M such that the smallest M letters in T are in the first row. So what I mean by that is you just want to find the largest M such that the sequence 1 through M in this case is going to be in the first row. Here we can see that 1 through 3 is in the first row, but 4 is not. So in this case, M is going to be 3. And then we delete the first M letters, the smallest M letters in that first row. In this case, we delete 1, 2, 3. We record that M is equal to 3. Now we detach that first row and add it to the top left corner of the remaining rows. So now we should have a shape that's like a partition shape and then some leftover of our first row. We swing that first row up to the top left corner to get a different skew shape. So here we take our 7, which is in our first row, we attach it here, and we leave this block unchanged. And then finally, you do the con to get a straight shape. So you just push your boxes in, push the empty boxes out until we get a partition shape again. And then you just repeat this process until we get an empty tableau. So that's why here in the first bullet point, I say find the largest M instead of 1 through M, because now our standard Young tableau is a tableau where each of our entries appears once, but we're missing the entries 1 through 3. So if we want to repeat what happens, our next step, we have 4 5s in our first row, so M is equal to 2. We delete them. There's no swinging involved, the row is empty. The next step, we have 7 6 8. We delete the 6. We switch the first row and the second row, and then we do the con. So we can repeat this process over and over again while keeping track of the number of boxes we delete at each step. The ith coordinate of our catabolizability type is the number of letters we delete in the ith iteration. So these M's that we've been keeping track of. Until we end up with, in this case, 3 2 1 1 1. So if you're familiar with what a catabolism is, what we've been secretly doing is applying catabolism to the standard Young tableau. The catabolizability type is encoding the sequence of catabolisms we use to go from a certain standard Young tableau to the 1-row tableau, where at each point the catabolism is lowering the charge by a certain, or the co-charge by a certain amount. But we don't need to use the catabolism definition here. We only care about how we're computing this sort of tuple. The nice thing is not only is this catabolizability type a tuple, it's actually going to be a partition. So if we pull up these definitions and we have this C-type relation here, they actually make sense because we're just comparing two partitions in dominance order. Here I'm just saying this catabolizability type associated to the standard Young tableau is greater than or equal to mu in the dominance order. To pull up the full picture, we have the Frobenius and the Hilbert series of our coinvariant rings. And we can see how, once again, the Garsia-Procesi, Frobenius, and Hilbert series are in fact summands of these bigger ones. Sorry, does that mean charge? Yeah, charge is invariant under Knuth move. Sorry, I just saw that. Yeah, essentially what the statement is saying is if you, yeah, it's a Knuth equivalent statistic. That's one of the properties of charge. Yeah, let's see. Yeah. So now that we have the full picture, we have our two rings, we have our two sets of Frobenius and Hilbert series. The natural question is, are there subsets of monomial basis of the covariant ring that are bases of the Garsia-Procesi ring? So for both of our classical monomial bases that we talked about earlier, this question has been answered. So Garsia-Procesi give a construction for the Artin basis, and Carlsson-Chou give a construction for the descent basis. However, the issue with these bases is neither of them have direct connections to the Frobenius character or the Hilbert series. So even though one nice property of the monomial bases of the coinvariant ring was that they were like super compatible with our Hilbert series, we don't have the same compatibility with either of these monomial bases of the Garsia-Procesi ring. So our natural question that we're considering here is to find a monomial basis of the Garsia-Procesi ring that is, one, a subset of the Artin basis and descent basis, and two, compatible with the Frobenius character and Hilbert series given here. And we answer this question by giving such construction. So we define our set of monomials using this sort of expression that appears in the Hilbert series. So we take monomials x to the CW, where CW is our charge word. So we're taking the exponent of a monomial indexed by W, or the permutation W, to be the charge word. And we're choosing our permutations such that they satisfy the catabolizability type condition from our Hilbert series. So some sort of miraculous result here is that this basis that we construct of charge monomials using catabolizability type coincides with the basis given by Carlsson and Chou. So I guess one thing to note here is Carlsson and Chou, they have a construction of their descent basis, but it involves shuffles of permutations. So they take a large set of inputs that are just like exponents of descent monomials, and then they just shuffle them all together. They shuffle them all together and they let the resulting set be their exponents of their basis. But one like big caveat to this method is because their input set is so big, it's hard to even show that the resulting set of monomials they get has the correct cardinality to be a basis in general. It's like non-trivial in their paper to show that they have the right number of monomials. Whereas for this construction, not only is it apparent that we have the right number of monomials, well, it's even apparent that we have the right number of monomials in each degree component. So this sort of like, even though we have the same basis, this construction highlights the nice connection to the Hilbert series and shows immediately that we have the right cardinality for it to be a basis. It's also super easy to compute. So let's compute a few examples to sort of see what's going on here. Let's let mu be at 2, 1, 1. I'm just going to give you a standard Young tableau that satisfies our catabolizability type condition. So the permutations we want are all permutations where our insertion tableau is the transpose of this. So we want all permutations with insertion tableau given by 1, 3, 4, 2. I've listed them out here for you. And now we know that for each such permutation, we're going to construct a monomial using its charge word. So we can look at this first one, 2, 1, 3, 4. Remember, we're reading from right to left, and we're labeling our numbers in order. So we start by labeling 1. We keep reading from right to left. We label 2 with 0 as well. We return to the front of the word. We see 3, so that gets labeled a 1. We have to return to the front of the word until we see 4, so then we label that with a 2. So that's how we get 0, 0, 1, 2. We just keep cycling through the word over and over again, adding 1 to the index whenever we reach the right end of the word. So similarly, we can do the same sort of construction for each of the other 2 permutations. And then I just smack those charge words into our exponents. So 0, 0, 1, 2 corresponds to the monomial. x1, 0, x2, 0, x3, x4 squared. So then just figuring out the permutations that satisfy the correct condition on insertion tableau is all you need to do. Once you do that, you just do this quick algorithm to figure out the charge word, and then you can construct the monomials. Why this basis nice? Well, not only is it nice because I'm saying it's nice, but there are actually nice properties associated to the basis. So one nice thing is it's a subset of the descent basis of the coinvariant ring. This is following from the fact that charge is secretly matched up to this change of permutations, as I was saying earlier. So it's easy to show that this monomial basis is indeed a subset of the descent basis. So that checks off our first bullet point in the list of questions we wanted to address. It's also compatible with the Hilbert series, as I've been saying, because the condition that we use to define our set is exactly the condition used in defining the sum of our Hilbert series. So once again, the number of terms in each degree is exactly going to match the Hilbert series. And I guess another thing to note is it definitely will match the degree because the degree of this charge monomial is just literally the charge of the permutation because the exponent is given by the charge word. And remember, the charge word is the sum of the entries in the charge word will give us charge. So just like from this construction, it's sort of immediate that this Hilbert series is correct and vice versa. From this Hilbert series, it's immediate that this gives us the correct number of terms in each degree. So we can also use this monomial basis to think about things related to the Frobenius character. So as I've been saying, oh, this basis is super nice. It's super compatible with the Hilbert series. But not only is it super compatible with the Hilbert series, but it's also compatible with the Frobenius character, i.e. we can use it to figure out the Frobenius character is given by our modified Hall-Littlewood polynomials. So for a certain representation, our Frobenius character is determined by the Hilbert series of this particular subspace of our module. What I mean by that is if we let n gamma be the sum over all permutations in the Young subgroup, except it's signed, we can think of n gamma as the anti-symmetrizer with respect to this subgroup. So n gamma v is just the anti-symmetric component of v with respect to a certain Young subgroup S gamma. Because the Hilbert series of this n gamma is just equivalent to the Hall inner product of E gamma with the Frobenius series. So what I'm saying here is these two are symmetric functions, and I'm just saying the Hilbert series of n gamma v is equivalent to taking the inner product of these two symmetric functions. And that gives us an expansion of our Frobenius character, so that determines the Frobenius character. So somehow computing or figuring out what the Frobenius character is boils down to, let's just figure out the Hilbert series of n gamma v for all possible n gammas we have. So the obvious way of computing the Hilbert series of these n gammas is just let's figure out a basis for it. And if we know what the basis is, we know what the dimensions are. So we do that here. We take our monomial basis of R mu, and then we don't look at all our monomials, we look at a certain subset. So we still have the same condition on the catabolizability type, but we have an additional condition here on the descent set of the permutation. So we want that the descent set is contained in the set determined by gamma. So we take a subset of the charge monomial that satisfies this descent condition. And then we just apply the anti-symmetrizer n gamma onto that monomial to produce a polynomial that's anti-symmetric. And we claim that this is going to give us the basis of our anti-symmetric component and gamma R mu. So once again, we sort of use our construction of the monomial basis to figure out what the correct anti-symmetric component is by just adding an extra condition on the descent set of the permutations we consider. This is sort of a natural set to consider when thinking about what we would want to expect from the modified Hall-Littlewood picture. So if you cheat a little and you sort of try to reverse engineer what's going on, you can see that the inner product between E gamma and this modified Hall-Littlewood polynomial can be written as the sum where we have the same two conditions, or we have the same condition on the catabolizability type and also have this condition on the descent type. So then if we can show that this n gamma set of monomials is indeed a basis, we do have that the Hilbert series exactly matches what we want from the modified Hall-Littlewood picture. So a direct corollary of this proposition is that the Frobenius character of R mu is indeed the modified Hall-Littlewood polynomial. And it's just following from this equality here. So somehow, which something that's rare in math has happened, of we have some things that we would like to be true just from reverse engineering. And then if we consider the first set of monomials from that expression, they work. So in this case, we just looked at the terms that appeared in this inner product, and we were like, oh, it'd be super nice if we could find a monomial basis index, or if we could find a basis indexed by these two conditions, and we actually do. The other nice thing about this sort of construction is it literally just boils down to looking at tableau. So for this case, let's consider mu being 2, 1, 1 and gamma being 2, 2. So if we go back to what we want our insertion tableau to satisfy catabolizability type greater than u. So in this case, there are 5 p that satisfy p transpose greater than 2, 1, 1. So it's given by these 5. Our second condition is on descent of permutations. Well, we have this very nice fact about RSK that the descent of a permutation is just descent of the recording tableau. So finding permutations that satisfy this descent set just corresponds to finding tableaux that satisfy that descent set and then setting that to be a recording tableau. So in this case, since our gamma is 2, 2, we just want to find 2 standard doing tableau where the descent set is contained in 2. There's actually only 2 of them. We have the 1 row and this hook. And now, because we want them to correspond to permutations, we want to construct pairs PQ, where P is in the first list, Q is in the second list, and they're the same shape. So there's literally only one possible pairing we can have. It's this first one and this third one. So this pair gives us one permutation. From the permutation, we can construct the charge monomial in the exact same way as we've been doing. So we take that word, we cycle around, we do 0, 0, 1, 2. And then finally, we apply the anti-symmetrizer with respect to, in this case, gamma 2, 2, to produce this polynomial. So figuring out the basis, once again, of n gamma R mu just boils down to looking at tableaux that satisfy 2 different conditions and then pairing them up so that they have the same shape, and then finding the monomials, applying the anti-symmetrizer. So even though this criteria itself looks very complicated, the actual way we go about computing these bases is just pure tableau combinatorics. That's it for what I wanted to talk about. Let me know if you have any questions. Here are some things I've been thinking about or planning on thinking about in the future.
Yes, thanks, Mitsuki. Questions? You're welcome to unmute and ask
Could you
questions.
go back to the page that shows why these are why monomials are nice? I guess that's
Oh, I can, yeah. Why is it nice? Okay.
yes, perfect, perfect. Okay. Yeah, those are nice qualities to have. That's so true. Okay. Yeah, I was just like sitting here, like, wait, I forget. This is very nice, but I'm like, wait, I can't remember why. Okay.
Yes. It's nice when we look at our questions. We're
Yeah.
just answering the questions we had.
Yeah. Yeah. That's great when we can do that.
We love answering our questions, yes.
Yeah. It's one of the best things to have to happen. Yeah. Okay. This is very, very nice and neat. Thank you.
Could you go back to the definition of n gamma? So it's let's see. So is it that cycle type? I think I missed the definition of gamma. So if it's like 2, then is it like
Yeah, so gamma is just, you can take a composition and you just take the Young subgroup corresponding to it. So each of the components is just given by the part of the composition.
Yeah. And how does this condition work? Like the gamma 1, gamma 1 plus gamma 2? Like is there
Like where does it come up or like?
Yeah, or is there like a more, you know, into the explanation, or where does it also
Yeah.
show up? Seems
Like I
kind of
guess the sort of natural way to come about it is like this is coming from the fact that if you look at the Koska number of lambda gamma, we classically think of it as like all semi-standard Young tableau of shape lambda weight gamma. But you can rewrite that condition to all standard Young tableau of shape lambda and then the set given by this thing here.
Oh.
So it's just like taking the semi-standard thing, and if you like take the standard version of the same picture, this descent thing sort of naturally comes up. And the reason why we do that is because we're dealing with standard things here. So instead of our classical definition of our Koska numbers, we want to deal with this sort of standard version.
Nice.
Yeah.
And
So it's like the natural thing.
Can you convert your results into semi-standard? Is there?
I think it shouldn't be too difficult. There are like a few things that are a bit concerning. Namely like there's a natural standardization of these like catabolizable standard Young tableau. So if you take all semi-standard Young tableau of a given weight mu, they biject into all standard Young tableaus satisfying this condition. So you should be able to go between the semi-standard picture and the standard picture just from that bijection, but it doesn't preserve things like charge words or like co-charge words very nicely. So like I'm assuming even if you do the same thing with a semi-standard picture, you will get the same basis.
But the X
But
to
you're
the
not going to have
CW will look uglier.
like either the CW looks uglier or like you have to do some sort of like it's not going to be like a one-to-one correspondence. Like the standardization corresponds to the exact same monomial. You might have to do some like finessing around to show why it works. I think the semi-standard picture fits better with the Carlsson-Chou result that I have here, where they talk about shuffles of things, because what they're essentially doing is they're considering semi-standard words, even though they don't phrase it in their work like that.
There's a question in the chat. Thanks for the nice talk, the other say. Do you have any intuition for how to do these? Do you have any intuition for how do these bases of the invariant ring behave if you also mod the non-face ideal of a nice simplicial complex, like a polytope, ball, or a sphere?
Oh, I don't know. I'm not super familiar, so I would be curious in learning, but yeah, I do not know.
Cool. Are there any more questions? Okay, if there are no more questions, let's thank Mitsuki again. I will stop the recording and then we can talk after that.